Today we're going to pick up exactly where we left off yesterday using that list of strategies. So we did 2 at the end of class, so you can just pick up where you left off and call this example number 3. Our goal is to simplify, no decimals allowed, and we're going to attempt to use that list of strategies to help us. So here's our first one for today. 5 to the 1/3 times 5 to the 3/2. 5 is already as low as base as it can get. You can't rewrite 5 as a lower base. What I would want you guys to notice on this example is that the bases are the same. So we can use the properties of exponents. When we multiply same bases, we are supposed to add the exponents together. So off to the side, you can do that work and get common denominators. So this will become 2/6 plus 9/6, which is 11/6. So if we add or multiply these two together, we will get 5 to the 11/6. That's it on that one. Next one, we're going to have 7 over 7 to the 1/3. 7 is also as low as a base as it can ever get, can't get lower. You can put an exponent in the numerator. That will be useful. So 7 is the same thing as 7 to the 1st power. So we again have same bases. When we are dividing same bases, we subtract the exponents. You could get common denominators for that, but you really should be able to do that mentally. If you have a whole and you subtract 1/3, you're going to end up with 2/3. So 7 divided by 7 to the 1/3 becomes 7 to the 2/3. And that is your answer. You cannot cancel out those 7s because of the exponents. The exponents are different. You cannot cancel those out. Okay, let's try this one. We're going to have 12 to the 1/3 over 4 to the 1/3 all squared. There's multiple ways that you could do this one. What I'm going to do first is I don't like that exponent on the outside, so I'm going to distribute it. So I'll get 12 to the 2/3 over 4 to the 2/3. From here, again, a couple different strategies. You could try to rewrite 4 as a lower base, but that'll ruin something that's good for us right now. And that's the fact that we have common exponents. That's one of our strategies. We have a common root, common power. So if I rewrote 4 as a lower base, then I would no longer have that common exponent. When I have the exponents in common, I'm now going to undistribute that from both, which will leave me with 12 divided by 4 to the 2/3, allowing me to actually divide 12 by 4. So 12 divided by 4 becomes 3 to the 2/3. And then just double check to see if you can actually use your charts here. Cube root of 3 is a decimal, so that's as far as it goes. Speaking of the charts, in 2 days you guys will have the quiz on this, so you got to make sure you're studying and making those flashcards because it's a no calculator quiz. Got to be ready for it. Next problem. Cube root of 4, so now we're in radical notation, times cube root of 16. For this type of problem, looking at our list of strategies, think about what I would want you to notice. And that would be that the roots are the same. So because the roots are the same, you can bring them under one radical. And 4 times 16 is 64. Now this just so happens that the cube root of 64 is a nice perfect value. If it wasn't, you could try breaking it apart again by finding a perfect cube that went into that number. But cube root of 64 is 4. Next one, cube root of 6 times 4th root of 6. Not the same root. Different roots, but they're the same base, same radicand. It would be easier to do this problem if we rewrote it in this format first, because then it'll be just like the first example we did today. So instead of writing it in radical, I can write it in rational exponent when the bases are the same to show you what you will then do. So multiplying same bases, just like in example 3, we're going to add our exponents. So we're doing a third plus a fourth. If I got common denominators, this would become 4/12 plus 3/12, which is 7/12. So we get 6 to the 7/12. And 6 is already a low base. You can't write that any lower. You can't rewrite 6 as a number to some power. We got 4 more today. 4 more examples. And then at the end of this video, I'm actually going to do the warm-up for tomorrow and one more example that I am going to do tomorrow. I just didn't want to make a separate video for that, for just 2 examples. All right, so for number 8, we are going to have, this one's going to look crazy, the 4th root of the square root of the cube root of 5. So we have a root underneath a root underneath a root. Looks scary, but once I show you how to break this up, it's not too bad. We're going to work our way from the inside to the outside and rewrite it in rational exponent notation for an example like this. So it's going to be first 5 to the 1/3 to the 1/2 to the 1/4. So cube root, then square root, and then 4th root. I now can then multiply all of these, power to a power rule, to get 5 to the 1/24. And 5 is a low base, and that is done. Fourth root of 256 xy to the 4th. Okay. For this problem, I'm going to rewrite it again in rational exponent notation. Unless I can right away see that I can break something apart, I always tend to rewrite it in rational exponent form. I think it's easier to use the properties in that format usually. From here, I'm going to distribute the 4th root to each of those individually and see what I can simplify down. So I will get 256 to the 1/4, x to the 1/4, and then y already had a 4th power, so when you multiply them, you just get y to the 1st. That allows me to 4th root them all individually. There is a 4th root of 256 if you look at your chart, it's a perfect value, and the 4th root of 256 is 4. So I get 4 x to the 1/4 times y. You can leave it in that notation, or if you wanted to put it back in radical notation, the 4 and the y are no longer under a radical, they don't have a root, and then it would be times the 4th root of x. X had to stay underneath that 4th root. So what we really just did, if we look back at the original problem, I took the 4th root of 256, and that came out as 4. And then if I 4th root a y to the 4th, that means there's one group of y's that can come out, okay? Because 4 goes into 4 one time. I can pull out one y. The best way I can relate that is if I had the 4th root of y to the 8th, that means I can pull out 2 groups of y's. So this would become y squared, because 4 goes into 8 2 times. So I'd be able to pull out 2 whole groups of y's. Two more. 5x to the 3/4 y times z to the negative 1/3 over 10x to the 1/5 y to the 3/4 z to the 2/3. So this kind of looks like the problems we were doing a few days ago with our properties of exponents. I don't like the fact that I have that negative exponent there. So before I try to do anything else, I would say move that to the denominator. So we're going to have a z to the 1/3 in the denominator. Okay, so you should try to get rid of those negative exponents. Then I can just use my normal properties of exponents. If I look across in the numerator, I can't do anything. So 5x to the 3/4 times y. But in the denominator, I can combine those z's. So I have z to the 2/3 times z to the 1/3. You're going to add those exponents, and 2/3 plus 1/3 is 3/3, which is 1 whole z. Then I could cancel downwards. The 5/10, they don't have an exponent, so you could divide them both by 5 to get 1/2. And the x's and the y's, we can do the canceling or subtraction method. So with the x's, I will have 3/4 minus 1/5. And with the y's, I will have 1 whole minus 3/4. So in the top, let's go ahead and do that. Get common denominators. So that will give me 15/20 minus 4/20, which is 11/20. It's a positive number, so that means my x's stay up top. So I will have x to 11/20. And technically, I didn't really need to write that coefficient of 1. Then the denominator, you should be able to do that with mental math. A whole minus 3/4 is 1/4. Again, it's positive, so the y's go in the numerator. And I still have that z to the 1st in the denominator. Let's pretend for a second that when you subtracted, you got a negative answer. When it's a negative answer, that means it would technically still go in the top at first. So say it was x to the negative 11/20. You'd put it up top, but because it's negative, then it would end up going to the denominator. So if you subtract and get a negative, you could just put it in the denominator right away. But if you're going to put it in the denominator, make sure you change it to a positive. Because when it moved down to the denominator, the exponent would become positive. So that's our answer. So still just using those properties of exponents. And the last one, so number 11, cube root of 40 minus cube root of 5. I'm going to have you guys look at your list of strategies for a minute and think about which one you would use for this example. Because this is a subtraction example, it has to be the fact that in order to add or subtract, it needs to be the same root and the same base. Right now it's not. So I can't do anything yet. However, I'm going to combine that fact with the fact that I could break apart radicals by looking for perfect factors. So cube root of 40. I can break that down into a perfect cube multiplied by another number. So our perfect cubes are 1, 8, 27, 64, etc. So I can break this into 8 times 5. That'll become 2 cube roots of 5 minus 1 cube root of 5. The coefficients are okay if those are different. It's just the root and the part underneath it, the base. So if I have 2 cube roots of 5 and I subtract 1 cube root of 5, that still leaves me with 1 cube root of 5. Think about this like if I had 2 x's and I minus 1x, then now I have 1x. So your radical is like a variable here. The 5 didn't change to something different. Okay. So that's it for today's examples. If there's any time left in class, at this point you guys can start the homework. I'm going to tell you to kind of stop the video. I'm going to do 2 more examples, but these are examples that you're going to do tomorrow. One is the warm-up, and one is just another example like this. So tomorrow's warm-up on the type 1, you guys are going to be asked to simplify this example. So I just want to explain this problem. Cube root of x times x to the 3/2 x to the negative 5/6 over square root of x. We have rational exponents and we have radicals. We really need to get them all into the same form. So I'm going to do two things at once. I'm going to rewrite them all in rational exponent notation, and I'm also going to move the one that has the negative exponent. We really shouldn't have that. So I'll have x to the 1/3, that's the cube root of x, x to the 3/2 over x to the 1/2, and x to the 5/6, because that moves down to the bottom. All of these have the same base, so I can either add my exponents or subtract my exponents. I'm going to add across first. So I'm going to first be doing 1/3 plus 3/2. If I get common denominators, multiplying the first one by 2, I'll get 2/6, and the second one by 3, 9/6, which is 11/6. So my top, I have x to the 11/6. And then the denominator, I'm doing 1/2 plus 5/6. I don't have to change the 5/6. I can just multiply the first fraction by 3. So that'll give me 3/6 plus 5/6, which is 8/6. Normally I would say simplify that, but the reason why I'm not going to simplify that fraction is I want the denominator to stay a 6 because I'm not done. Because now that I'm dividing same bases, I'm going to have to subtract the exponents. So just leave the denominators the same. That saves you a step. So if I subtract, I'm doing 11/6 minus 8/6, which is 3/6, and that simplifies to 1/2. So now we can simplify because we're at the end. So my final answer is x to the 1/2, or you can write that in radical notation as the square root of x. So that's the warm-up. And the one additional example that we're going to do today, and this was actually taken from a Smarter Balance released item, and even though you guys don't take Smarter Balance for math in high school anymore, I still think it's a good question. So this last example, if I gave you 5th root of a to the 4th times cube root of a squared, and that has to equal a to the n. So we're essentially trying to figure out what n is equal to by simplifying this left-hand side. Right now the roots are different, so you can't combine them under 1. So I would suggest to rewrite this in rational exponent notation since you can't combine them together. So this would become a to the 4/5 times a to the 2/3. I'm ignoring the a to the n right now. I'm multiplying same bases. That means I can add my exponents together. So I can do 4/5 plus 2/3 and get my common denominator. So I will get 12/15 plus 10/15, which is 22/15. That cannot be simplified at all. Therefore, the answer to this question, if when I simplify the left-hand side, I get a to the 22/15, and that's supposed to equal a to the n, therefore n has to be 22/15. And that's how you would go about that. And that's like, even though this was from the Smarter Balance, this is also a very typical SAT type question. All right, so those were the two examples for today. Today's day 5, and it is the last day of this section. Tomorrow you guys will have a quiz, so if you haven't made flashcards already, you really need to be making them tonight and quizzing yourself to make sure you're familiar with the numbers on that chart. And you can take roots at any time, as well as practice on the type 3 to make sure you can apply these strategies to the wider range of different scenarios that you could be presented with. So type 3 also has some SAT practice on it, which is good exposure. And that's it for this section.